So we've got exam 4 coming up on chapters 14 and 15, acids and bases. And that includes discussions of equilibrium and buffers, especially in chapter 15. So let's look at the way the review document is, review documents are divided. There's one for chapter 14 and one chapter 15. So we'll do chapter 14 first and work our way through some of those problems. And then we'll look at chapter 15. So let's see, I've got some picked out here. First three. Which of the following is a conjugate acid-base pair? Remember what we were talking about, what I was talking about. The definition of a conjugate acid-base pair is, in order to have a conjugate base of an acid, say our acid has 2 protons. We only dissociate 1 proton at a time. So that means one of these will leave and we'll have that left over. And then the proton will transfer over to water and produce our hydronium ion. So that makes this the acid. And this is the conjugate base of that acid. That's true for any acid. If you have 1 proton, then it's easy. You just lose the proton and you have the conjugate base left over. But the key is only 1 proton at a time, and this part of the molecule does not change. Right, so let's look at our choices. If we have this one and that one, what do we have here? Which one's the acid? Well, there's the proton, so that has to be the acid. So what's the conjugate base of this acid? If it loses a proton, what's left over? If it loses a proton, we have that left over. And these two are not the same. Can't be. So A is not the answer. How about B? H2SO4 and SO4 2 minus. Okay? What's wrong with this picture? Well, obviously, these are the same, but we've lost 2 protons to get there. That's wrong also. What is the conjugate base of this one? HSO4 minus, right? So those can't be. How about C? NH4 plus and NH3. Okay. You'll recognize this one as the ammonium ion, which is a polyatomic ion and is the only positive polyatomic ion that we discuss in this class. First introduced in Chem 101. But if this one behaves as an acid, it has to lose one of those protons. Right? So it will do this number and transfer a proton to water. That looks perfect to me. We lost 1 proton, ended up on water. So this is the conjugate base of that acid. Now, as a matter of fact, ammonia behaves in such a way that it prefers to be ammonia, not ammonium. So if you put this in solution, it's going to be almost exclusively NH3. So the equilibrium is shifted way to the right for this particular species. Okay, so we found our answer. And we might as well look at D also, just to be complete. So if you have the hydronium ion and you're comparing it to the hydroxyl, what does the hydronium ion do when it loses a proton? Well, if we write it in a simplified version, then one proton is lost and you have water. So the conjugate base of H3O plus is H2O. So that can't be. Okay, so that was number one. We were just discussing I was just talking about what constitutes a conjugate acid-base pair. And it's really simple. When you have an acid, you recognize the extra proton. And we always lose one proton at a time. So a conjugate base of an acid can only be what's left over after that one proton leaves. And you're always also looking for these parts of the molecules to be the same on both sides. That's why this one fails, right? OCl minus can't work. It's got to be Cl minus for hydrochloric acid. This one can't work because it loses two protons to get the sulfate. So that's wrong. This one, we don't often think of the polyatomic ion, NH4 plus, ammonium, as being an acid, but it can lose a proton. And if it reacts with water, it will transfer that proton. And that looks too much like a plus on the molecule. There we go. Leaves us with ammonia and hydronium. So that was perfect. It lost one proton over here. This is the conjugate base of that acid. So the answer to this one is C, and I was just looking at D to be complete. The hydronium ion, when it loses a proton, ends up as water. So water is the conjugate base of the hydronium and not OH minus. In order to get to OH minus, we would have to lose two protons. Actually, we'd have to lose, yeah, that's right, two protons would give us OH minus. And that's wrong for the same reason as sulfuric acid is wrong. Okay, that was number one. We start off slow, gather a little speed as we go. We'll look at number two also. The hydrogen sulfate or bisulfate ion, this is the old nomenclature, bisulfate. Bi just means the sulfate has a hydrogen added to it. They can act as either acid or base, in aqueous solution. In which of the following equations does HSO4 minus act as an acid? Okay, so in order to be an acid, HSO4 would have to do what? Well, if we use a complete reaction and not the abbreviated form, then this hydrogen would have to transfer, right? According to Bronsted and Lowry, the acid is the one that loses the proton. So this proton would have to transfer to that water, and that would give us the hydronium ion plus whatever's left over here. And when a proton leaves, it leaves behind its electrons. So that means SO4 has a 2 minus charge. So which one satisfies that one? Here we go. Looks like D. D would be the satisfactory explanation for HSO4 minus as an acid. Okay. As usual, I picked out some out of the review document, and 3, let's look at 3. Which of the following is the equilibrium constant expression for the dissociation of the weak acid HOCl? So we want the dissociation constant, or the Ka, for HOCl. Okay? You'll notice that each one of these has the separate proton. We're not using hydroniums, so we need to use the abbreviated form. So the dissociation of this, we exclude water, except it's just the phase is included. So it has to lose 1 proton. And what's left over? That. And it's all an aqueous solution. Can we keep each one of these? Well, yeah, they're all aqueous solutions, so their concentration matters for the dissociation constant, Ka. So we need this one, proton concentration. What is OCl minus anyway? Right, remember from your polyatomic ion list? The way I set it up was, actually I set it up the other way. I set it up like this: ClO3, ClO2, ClO, and ClO4, each one with a minus. This is the chlorate polyatomic. This is the chlorite. This is the hypochlorite. So that's the hypochlorite ion. It just has the oxygen and chlorine flipped. And then to complete this expression, we need the concentration of the acid. Okay, so that one should be up there somewhere. Looks like it's the first one. Okay, and they're right, it is a weak acid. And the name of the acid, if that's the hypochlorite, then the acid would be, we don't say hydro, so we just take the anion, and if it's us, if it's I, it becomes us. So hypochlorous acid is that compound. All right, that was number 3, with a little extra thrown in for free. Let's see. Well, oh, here we go. Let's see if I can get to it by paging. Up to 5. Now I'm going to have to scroll. Let's see about that. Then maybe I can page to the next, because I want to do 5, 6, 7. 5, no, not 5. I want to do 6, excuse me. 6. There we go. About that. Then maybe I can page to number 9, because I want to do 6, 7, 8, and 9. There's 6. A solution in which the pOH is 12.1. So we're given this much information. Would be described as what? Very acidic, slightly acidic, neutral, very basic, slightly basic. How do we know? Well, our scale that requires some intuition and familiarity is based upon pH, not on pOH. So if we find pH, then that is a better information for answering this question. So if pOH is 12.1, what's pH? Well, remember, pKw is equal to 14, and that's also equal to pH plus POH. That was our shortcut method. So what we need is to plug in 12.1 in here. That means subtract it from 14, and that give us pH. 1.9 equals pH. Now that makes more sense to answer this question. It's very, very low pH. So we would say it's very acidic. Right? Neutral is 7, and the pH scale is good down to about 1, or up to about 12, 12 and a half, something like that. Beyond that, it's probably better to use concentrations. Although you can calculate pH or POH, it's just the negative log of the concentration, right? It's just a mathematical transformation. So you can calculate those values for any concentration of either hydrogen ions or hydroxyl ions. Or for the K values. But as a practical matter, we generally try to restrict the use of pH in the positive range from about 1 to 12 and a half. That was 6. Let's see. We're going to do 7 also. Which of the following indicates the most basic solution? All right, so in this case, we've got apples and oranges here. A, B, C, and D are different, right? They're all different units of measure. So we've got to find a common unit and then settle on it. So which of the following indicates the most basic solution? We're going to work on that scale again, the acid-base scale, then it might be most efficient to convert everything to pH. So if we do that, A is hydrogen ion concentration is 1 times 10 to the minus 10 molar, right? And pH should be, we can do this in our head because that's 1. So we only have to deal with 10 to the minus 10. So the pH of this one would be 10. Okay? About B, POH. So POH is equal to 6.7. And then pH is equal to 14. Oh, excuse me. Not 14.1, it's 14. I don't know where I got 14.1. I hope I did that one right before. I'll see on the video. 14 minus 6.7. Okay, so that means the pH would be, let's see, 0.3, and then 6 and 13 is 7. 7.3. Okay, let's see. OH concentration is 7 times 10 to the minus 5 molar. We have two choices here. We can use our equilibrium equation, Kw equals concentration of hydrogen ions times concentration of hydroxyls. Or we can go ahead and convert this to POH and then subtract it from 14, and that's the one I prefer. So if we convert that to POH, okay, we're just going to take negative log of 7 times 10 to the minus 5 molar. So 7 exponent 5, change the sign, and then take the log of that, and then change the sign. So I get 4.15. Well, yeah, we only got one significant figure. I'm going to hang on to a couple here, just to avoid rounding error. So this is 4.2. POH. And pH is equal to 14 minus 4.2 or 8, 9.8, or rounded off to 10. But we're only doing comparisons here, right? So all we need to do is it different than something else? And then D is already pH 4.2. Okay, now we can compare. Which is the most basic? We have a pH of 10, 7.3, which is almost neutral, and a pH of 9.8, a pH 4.2. Now, there are two possibilities for this one. If you keep that extra decimal here, which technically speaking is not correct because there's only one significant figure here. Oh, no. We're working with logs. We're working with logs. So the log rule says that if we have the number of decimals is equal to the number of significant figures in the original number. So we have one significant figure, which means we keep one decimal. So this is correct, 4.2. All right, let me say that again. You start off with a number here that has one significant figure, then the transform can have one decimal. It's the nature of logarithms. So this one decimal says that that is one significant figure. So by subtracting 4.2 from 14, we get 9.8. So if you don't remember that rule, then you might think that C should give you a pH of 4. You should round to one significant figure here, but it's a log transform, so it has to have one decimal. And that's what this E is in there for, to check to see if you remember that rule. Because if you don't, then you're going to say that this one is 10 and that one is 10. And then you're going to say at least two of the solutions are equally basic when they're not. So A is the most basic solution here. Actually, that's got one significant figure. This should be 10.0. Okay. Let's see, that was 7. We'll go to 8. Which of the following solutions contains the strongest acid? Okay, we've got to remember the definition of acid strength. The definition of acid strength is how far is it to the right in its dissociation. So if we say HA dissociates into a proton plus an A minus, how far does it go to that side? Which means the Ka for that would be, well, if we just write it out like this, that divided by this, then this would be, for a very strong acid, it's much, much greater than 1. In other words, we're way to the right. Okay, so the one that has the largest K value will be the strongest acid. All right, so let's look at it. Let's see, and it doesn't matter here, except we might look at this one because it has two K values and say, which one determines the pH of that aqueous solution? And this dissociation for the first proton is that value, for the second proton is that value. And look, it's 7 orders of magnitude smaller. So this one has no impact on the pH, right? We can ignore that one. And we just focus on the first K values. All right, so which one has, and the concentration doesn't matter. We're talking about strength. We're not talking about pH or acid concentration. We're talking about the strength of the acid. So if we compare these K values, which one is the biggest? Okay, there's -10, there's -5, -5, -8, -4. 10 to the -4 is the largest K value in that group. So E, HF, is the strongest acid in that group. Now, they're all weak acids, right? Just look at the K values. They're all weak acids. Now, when I misspoke here. It's much, much greater than 1 if it is, in fact, a strong acid. But these are weak acids, and we're looking for the strongest of the weak. So we just compare the K values for the pH determining proton. And that says that we have to focus on this one here and the rest compared to it. And HF is the strongest acid in that group. Okay, let's see if I can page down to number 9. Here we go. Which of the following statements are true? Okay, so we've got to go through all of them. Actually, we have to go through 3 because D and E are compilations. They're based upon the answers to A, B, and C. So let's see, which of the statements are true? How about A? The pH of a strong acid is always lower than the pH of a weak acid. Is that true? What determines the pH? It's a negative log of the hydrogen ion concentration. Is it possible to have a lower pH for a weak acid than the pH for a strong acid? Yeah, because we're talking about equilibrium position now. When you're talking about hydrogen ion concentration, you're saying that if the strong acid starts off at a very, very, very low concentration versus the weak acid that starts off at a very high concentration, it's possible to have a lower pH for the weak acid than for the strong acid. Right? So this one, the pH of a strong acid is always lower than the pH of a weak acid, is a false statement. Okay. That one's wrong. It is possible to have a lower pH for a weak acid than a strong acid. It all depends on concentration. How about B? The pH of a solution can never be negative. Never. pH, never negative. Is that true? I think I demonstrated that one in class. Right? This is a log transformation. Right? All you need is a concentration here that's high enough to give you a negative value for this term. Right? So that one's false. You can have negative values of negative log hydrogen ion concentration simply because it's a mathematical transformation. So anything's possible. You just need the right concentration here to give you a negative number. I think I used maybe 1 molar hydrochloric acid. If you put 1 molar in here, that's 0, right? 1 molar. So the log of 1 is 0, right? 10 to the 0 is equal to 1. Right? So that's a bad choice. because that's not negative. How about, let's see. What about 0.1 molar? That'd be 10 to the minus 1. So the log of that one would be minus, no, that'd be plus 1. How about 2 molar? There we go. So 2 molar would give, well, I can't do that with my head. How about 10 molar? 10 to the first power is the log of 10. Okay, so that would be, the term would be 1 here and a minus 1. There you go. So 10 molar hydrochloric acid would give you a minus 1 pH. Oh, I got more to do. C. This one's false. So let's look at C. For a conjugate acid-base pair, Ka equals 1 over Kb. Ka 1 over Kb. Is that true? No, we know how to determine Kb from Ka, don't we? Because Kw equals Ka times Kb. We proved that during the lecture, actually. So Ka then would be equal to Kw divided by Kb. That's not the same as this one. So the correct answer here is E. All those statements are false. Okay, that was 9. I'm going to go to 11. Let's see if I can get there with the paging. There it is, 11. Okay. For the stepwise dissociation of H3PO4 in aqueous solution, what's that called? Phosphoric acid. It's an aqueous solution. That's phosphoric acid. For the stepwise dissociation, which of the following is not a conjugate acid-base pair? Okay, let's do the stepwise dissociation. And we'll do it abbreviated form. Right, so the first dissociation is what? 1 proton, and then H2PO4 minus. And this one comes over here. And it loses a proton. Now it's HPO4 2 minus. Now that one comes over here. HPO4 2 minus loses a proton and becomes PO4 3 minus. Get a new marker. That was failing. Let's see about this one. Yeah, it might work better. Okay, which of the following is not a conjugate acid-base pair? Okay, so what do we have? We have, these are all the acids, and these are all the conjugate bases. Right? So, there we go. No, that's not the one I was on. I was on 11. There we go. So how about the first one? Which of the following is not a conjugate acid-base pair? Right. So HPO4 2 minus. Here, this is our acid, and the conjugate base is PO4 3 minus. That one's true. How about this one? The second one. B is H3PO4, H2PO4 minus. B is true. Then H2PO4 minus gives you HPO4 2 minus. That's true. acid-base pair. And then D, H2PO4 minus, and PO4 3 minus is for this one, not that one. So D is false. And then I think this one was just thrown in for fun. I couldn't think of another one. Is this true? H3O plus, H2O. So we have to draw it out. H3O plus loses a proton, and then H2O. That's true. Now, why was this one thrown in there? For the stepwise dissociation of aqueous, well, you might think it's not fair to put that one in there because it's not the stepwise dissociation of H3PO4, except, remember, in aqueous solution, this reaction is always happening. No matter what's going on here, this one is always there. And it has its K value of 10 to the minus 14. Okay, so I think that's the reason this one was thrown in there. Just to spark your memory and say, yes, that's true. No matter what happens up here, that's always true. All right, so that was 11, I think. See, what's the next one? I had 12 marked also. Yeah, I need to scroll just a little bit. Here we go. For 12. Okay, for which of the following 0.1 molar diprotic acids would the second dissociation affect the pH significantly? Okay, so each one of these is 0.1 molar, and they're diprotic. And we're using generic formulas for these. H2A, B, C, D. I guess it corresponds to their answer letters. But what you want to look for here is how far apart are the two K values. Ka1 is this value, Ka2 is that value. You look at the spread. Right? If this one is 10 to the minus 2 and the second one is 10 to the minus 7, that's 5 orders of magnitude. 1, 2, 3, 4. That's 100,000 times smaller. Right? So that one will have no impact on the pH. It's all due to this one right here. And we showed that during class when we were discussing phosphoric acid and the K values for phosphoric. They were about 5 orders of magnitude different, one to another. And we found out that the first one is the only one that affects pH. So this one doesn't. The second one does not affect the first one. How about this one? It's 4 orders of magnitude different. It won't have an impact either. How about this one? That's 5 orders of magnitude different. Right? I always use that term. Do you understand what I mean by order of magnitude? Power of 10. Right? That's the order of magnitude in science talk. And this one is -3 and that one's -4. They are very close together. This is only 1/10 different. And if you look at that value, the coefficient for the number, right? Let's write this one out. D, right? Ka1 is 1.8 times 10 to the minus 3. And Ka2 is 9.3 times 10 to the minus 4. Okay. So let's put these in standard notation. So we need to move the decimal place 3 to the left, right? It starts here, 1, 2, 3, right there. How about this one? 1, 2, 3, 4, even another one, and 9, 3. So we're starting right here. 1, 2, 3, 4. Let's go. Now, how do these compare? Well, this one is in the 4th position. What if we double this one? Just say 2 times that. Okay. So this one is actually not 10 times smaller. It's only half the size. About half the size of this one. So it's very close. Those K values are very close together. There's only a times 2 spread. So this one will have a significant impact on the pH of that solution. That's why D is the answer for this one. All right, need a wet whistle. Next, I want to look at, let's see, this page down, 16. So while I'm here, I'm just scrolling. There's 16. Okay. Which of the following would give the highest pH when dissolved in water to form a 0.1 molar solution? We got a 0.1 molar solution of these possible compounds: strong acid, weak acid, potassium salt of a weak acid, potassium salt of a strong acid, ammonium salt of a strong acid. Okay, so we've got this molar concentration of any one of those. Okay, first we have a strong acid. Strong acid, a weak acid, a potassium salt of a weak acid, or potassium salt of a strong acid, or ammonium salt. Of a strong acid. Okay. So if we have a strong acid, and I mean definitely strong, the K value is close to infinity, like hydrochloric acid. That strong acid would have a pH of 1 based on that concentration, right? 10 to the minus 1, negative log of that value is 1. Now the rest of them are not as easy. We can do that one because that's the nature of strong acids. They're completely dissociated. Weak acid is going to have a higher pH than that. But we want the highest pH. The weak acid is still going to be pH less than 7 because it's an acid. It may only dissociate a little bit, but it's still going to give you a pH. It may be very close to 7. It may not be strong enough to overcome or compete with the pH controlling of water dissociation. So it could actually be equal to 7. Depends on how weak it is. Okay, how about the potassium salt of a weak acid? What does that mean? Potassium salt of a weak acid. when it goes into solution, what does it make? It makes potassium and the weak acid. The conjugate base of the weak acid. All right. So what do we say about conjugate bases of weak acids? They're very strong bases. So this is a strong base. Okay. The potassium salt of a strong acid. Well, potassium hydroxide is a strong base, and your strong acid together, remember what we said about that? Strong acid, strong base together, this is neutral. That one. How about ammonium salt of a strong acid? Well, in that case, we've got a ammonium from a weak base, ammonium hydroxide, and a strong acid. And the rule of thumb is weak base, strong acid, salt dissolved in water favors acidic. So the pH here is less than 7. Okay? So now we can answer the question, I think, right? Which of the following has the highest pH? Oh, we didn't say pH for this one. If this is a very strong base, right? When we put it in solution, it comes from a weak acid, so that's a strong base. This pH is going to be greater than 7. Now, how much greater than 7? It depends on the weakness of the acid for this conjugate base. Now, I say this conjugate base is not related to this. This is the conjugate base of that weak acid. Okay, that's what I'm talking about. So that makes this a very strong base. And the pH here is going to be actually the only one that's greater than 7 out of that bunch. Right? That's why C is the answer. Okay? All right, let's see. 16. How about 19? Well, 19 requires this statement. This statement is for 17 through 20. So we need to get this statement and then go to 19. Select the answer that best describes an aqueous solution made from each of the following substances. So we're going to make an aqueous solution from solid ammonium acetate. Okay? And the Ka for ammonium is 10 to the minus 10, and the Kb for this conjugate base of acetic acid is the same, exactly the same number. Right? So we didn't dig into this very deeply during a lecture, but when the Ka of the cation is equal in magnitude to the Kb of the anion, you get a neutral solution. They're competing, right? This one is competing to release protons. This is competing to extract protons from water. So the competition is perfectly balanced. You just balance the Ka of the cation with the Kb of the anion. And this would be a neutral solution. Now here. And yes, we can tell what it is. In fact, that's the only way that you can tell what the pH is of a salt made from a weak acid and a weak base. All right. 19. Let's see. We can do any more on that one? Yeah, I got 20. Let's look at 20. It's based upon that same. We're going to make a solution out of solid ammonium perchlorate. Okay. So what's ammonium perchlorate? NH4 is ammonium, right? Perchlorate ion is ClO4 minus. So one of each is all you need. Well, it gives us the formula right there. That was nice of one. We didn't even have to deduce it. But this is going into solution. Okay. So what's it going to make? It's going to make ammonium ions and perchlorate ions. Okay. And this goes completely into solution. It's soluble, completely soluble. So actually, you're starting off with these ions. And what we want to do is say, what's the pH of this solution? All right. So we need to say, all right, which is the competition here? If we say Ka for NH4 plus, what does that mean? Right? So that in solution, this is what that's going to do. And if we write out the complete reaction, this is going to transfer that proton over to water and make hydronium, right? And that K value is 5.6 times 10 to the minus 10. 5.6 times 10 to the minus 10 is the Ka for that reaction. The Kb for this one is 10 to the minus 21. So the Kb would be ClO4 minus plus water. And the Kb transfers a proton from water to this species. Think of it this way. When you get an anion going into solution, it's going to react with water. And if it strips a proton from water, what do you have left over? Hydroxyl. That's where the basic nature comes from. So that's why we call it Kb. So now we have this one, HClO4. That's perchloric acid. That's a strong acid. And the Kb confirms it's approximately equal to 10 to the minus 21, right? So when these this cation and this anion are in aqueous solution, these are the competing reactions. This one goes there, and this one goes there. So which one has the greatest equilibrium to the right? This one does. And if this one has the greater equilibrium to the right, it produces acid conditions. So if we compare these two numbers, we find that this one is dominant and produces an acidic solution. That's why the answer here is A. Okay? If we had a situation where the Ka for one was reversed, right? Maybe we had 10 to the minus 15 here, and for the Kb for the other one, you have 10 to the minus 5. Then it would be a basic solution. It's a competition between these two reactions. Actually, it goes back to that, the rule for deciding how to determine pH is first you start off with what are the major species in solution. And the major species in this case were ammonium and perchlorate ion. Then you go from there because what do they do? What do they react with? Well, the other major species is H2O. So that's how they're going to react. Okay, that was 20. How about 22? There it is. Let's see, how am I doing on time? A little after 9. This class goes for what, 9:50? Where is it? Oh, 10:50. Good, good. Okay. I don't want to run out of time because I still haven't got chapter 15 yet. All right, 22. Which factor listed below is most important in determining the strength of an oxyacid? First of all, what's an oxyacid? Well, it's got to be an acid, right? Got to have at least one of those. And then the rest of the molecule, the A part, has oxygen in it. So it's going to be a polyatomic ion. So for instance, if we had chlorine there, this could be a 1. If that's a plus, this is a minus, that's a minus. It could be this one. It could be this one. Or it could be this one. Right? Any one of those. Oops. Boy, that was a boner. Okay. So I got to regain my composure. So which one of these is the strongest? Just as an example, this one right here. By definition, the strength of an oxyacid increases as the number of oxygens in the polyatomic ion increase. So this would be the same for if we had this one, right? Nitric acid would be stronger than nitrous acid. Or let's see, SO4, let's do it. Let's keep it uniform. SO3, 2 minus, or SO4, 2 minus. Sulfuric acid would be stronger than sulfurous acid. It has more oxygens in it. That's why the answer is D. The number of oxygen atoms present in the molecule determines the strength of the acid. That's 22. Let's see, I've marked off 24. Yeah, chopped off the bottom answer. There we go. 24. All right. Which of the species below, when dissolved in water, will not produce a basic solution? All right, so let's look at it. A, B, C, D, and E is none of these. Okay, so we're going to dissolve these in water. NH3 is in BaO aqueous. I'm on the right one, 24. Yeah, okay. BaO and BaOH2. Okay. Which one will not produce a basic solution? So let's see. Which ones do produce basic solutions? Well, based upon the Arrhenius model, right? The molecule that has hydroxyls in it will produce a basic solution. That's not Bronsted-Lowry. That's the earlier version. If it's got hydroxyls in it, yeah, that's basic. Right? Because of those. Okay. Let's keep working our way up. How about this one? What is it going to do when it gets in water? This one is going to dissociate and release those hydroxyls. That will make a basic solution. But what does this one do in aqueous solution? Well, it reacts with water. Right? And what does it do? Well, it strips a proton off of there and makes BaOH plus OH minus. So actually, It makes lots of OH minuses too, because this one is also going to dissociate. So you've got that one and that one. So this one's basic. How about this one? What does it do in water? I think I used this one early on when I was describing the need for Bronsted and Lowry definition, right? Because there are no hydroxyls in that molecule. So it reacts with water, and it strips a proton off of water and produces the ammonium ion plus hydroxyls, right? There's your basic solution. Okay? How about this one? This is one of those, the tail end of the chapter. I think it was just chapter 14. We described molecules that had oxygen on them, what happens in water. One type is metal oxides, or they call them anhydrides. And these are non-metal anhydrides. So when we say anhydride, that means water was removed from it originally. That's one way of thinking of it. So if we remove water from this one, it brings us back to that one. But when we add water to it, we rehydrate it. So rehydrating this one does what? Right? Well, the oxygen goes in here and adds to those O's, 3. Then we have the sulfur, and then we have the 2 hydrogens. So we have sulfurous acid. That was the only one that's not basic. And this is characteristic of any non-metal oxide. When you put it in solution, it will go through a similar reaction and make an acid. Right, so SO2 is the acidic one, and the rest of them are basic, and E doesn't count because it says none of these. Yeah, there is one. That one is acidic. Okay? That was 24. Let's see, 24, flip the page. Let's see, do I want to do 25, 6, and 7? They're along similar lines. 25, let me scroll up so we can get them all on the page at the same time. There we go. 25, 6, and 7. 25. Which of the following species cannot act as a Lewis base? So what is a Lewis base? Okay. Well, think of it in these terms. Bronsted-Lowry says that an acid is a proton donor. So it's going to, I don't know, keep it in water. And it's going to donate that proton to water. Okay? If that's an acid, what happened to the electrons in that reaction? Well, the electrons were received by the A to make this. So an electron pair was received by A, which makes it an acid. So a proton donor is also an electron pair acceptor. And that is the Lewis acid. An electron pair acceptor. Okay. The reason I went through that discussion was, now that we know what an acid is, the base is just the opposite. Or the converse, I should say. The Lewis base is an electron pair donor. So the species that we're interested in determining here, Lewis base, it has to be an electron pair donor. If it cannot donate a pair of electrons, then it cannot be a Lewis base. Okay, so let's look at these. Can O2 minus donate a pair of electrons? Well, yeah, it's got plenty. Right? If it donates those 2 electrons, now it's a single atom of oxygen. How about this one? OH minus? Well, yeah, it's a negative charge. It can donate a pair of electrons. How about CH4? Look at it this way. CH4. All right, what do we got here? Well, if we write the Lewis dot structure, which is the best way to approach this, right? You have 4 valence electrons here, and 4 times 1 is 4 there, so we have 8. And then we do like this, this. Right? I'm just writing the Lewis dot structure, following the rules. 2, 4, 6, 8, they're all used up. Right? Are there any electrons here that are available for donation? No. They're all occupied in bonds. H2S. Right. Well, H2S is like this one. So how could it act as could a H2S act as a Lewis base? Hold on a second. We know that methane can't work, but what about H2S? Well, let's see. We got 2 valence there, and sulfur is in the same group as oxygen, I believe. Right? So it has 6. That means we have 8. So S, H, 2, 4. So we have 4 electrons left over. That's as far as we need to go. I mean, we don't have to go to the structure to answer this question. You've got 2 pair of non-bonded electrons. Those are available for donation. This would be an excellent Lewis base. How about NH3? All right, let's do NH3. Ammonia in solution would be like this. We have, 5? Yep, 5 here and 3 here means 8. Right, so we got this. 2, 4, 6. So we have 2 electrons left over. They have to go here. There's another pair. This would make an excellent Lewis base. Has those free pair of electrons, non-bonded. Okay? So that's why the answer here is cannot act as a Lewis base is methane. That was 25. Let's see, 26. Oh, we got another one. Cannot act as a Lewis base for 26. How about this one? Right. So we use the same logic as 25. We need one that can donate a pair of electrons. Right. Look at all those charges. Donate those pairs of electrons. This one we already did, ammonia. Yeah, it's got an extra pair of non-bonded electrons, right? Any one of these could donate a pair. How about NH4? That's the key. Okay. So we have nitrogen is 5, and then we have 4 for hydrogen, and then we have a positive charge, which means we have to subtract 1. Right? So instead of 9, we have 8. And so here we have N, H, 2, 4, 6, 8, all gone. So that ion will not act as a Lewis base. It has no free electrons to donate, no non-bonded pairs. All right, so that's why the answer is E for 26. 27. All right, we're going to look at Lewis acid. Which one cannot act as a Lewis acid? That is, which one doesn't want a pair of electrons? Remember, Lewis acid accepts an electron pair. So which one of these would accept an electron pair? Any positive ion is going to accept the electrons. So potassium, magnesium, aluminum, hydrogen even would act as a Lewis acid. It would accept an electron pair. Okay, but the hydrogen, the negative hydrogen ion will not accept any more electrons. It's not a Lewis acid. It would make a Lewis base, yeah. Probably a good one, but not a Lewis acid, right? So that's why the answer here is E. All right. So 27, which one did I go to next? 29. I'll just scroll down to that one. There we go. In this reaction, calcium oxide and sulfur dioxide yield calcium sulfite. Oh, we're still on acid base, Lewis acid, Lewis base. Okay. So let's see. Here's our reaction, calcium oxide, solid, plus sulfur dioxide yields calcium sulfite, solid. Okay. So before we look at the answers, let's look at the reaction. What's going on here, right? Apparently, there's no water involved, right? So we can't use aqueous solution as our starting point. This is solid, gas, solid. So what do we have here? Well, oxygen is 2 minus, oxidation state for each, 2 minus, 2 plus. This one is 2 minus, this one is 4 plus. Right? 2 times 2 minus is 4 minus, has to be balanced with a 4 plus. This one is also 2 minus. This one is 2 minus, which means 6 minus, and let's see, 6 minus, and 6 minus and 2 minus is 8 minus. So that means this is 8 plus. Okay? So what has happened here? We can look at this in redox terms also. That might help us answer the question. Sulfur has gone from here to here by a loss of 4 electrons per sulfur. Okay? Oh, wait a minute. That's not right. That's not right. Hold on a second. Calcium is 2 plus. Right? Right, so this is 6 minus and 2 plus is 4 minus, which is 4 plus. No redox effect has occurred for a sulfur. Okay. So let's look at it this way. If we draw the Lewis dot structures for these, will that answer the question for us? Right? Let's leave redox behind. That was a dead end. Simply because there's no redox reaction here. What about calcium oxide? Can we write a Lewis dot structure for that? Well, let's see. Calcium has 2 valence electrons, oxygen has 2, so that's 4. Well, actually, this is an ionic compound. So this one is going to be 2 plus, and this is 2 minus. Where are the electrons? Well, the electrons are over here on oxygen. This one, we can draw a Lewis dot structure for that one. In fact, we did that before, I believe. Didn't we? No, that was different. Let's do it methodically here. Sulfur is 6 electrons, oxygen is 6. So that's 12, and that's 18 electrons. Okay, right. We didn't do that one before. So that's 2, 4. That means we have 14 electrons. 2, 4, 6, 8, 10, 12, 14. Okay, so sulfur dioxide can act as a Lewis acid. No, and it can act as a Lewis base, right? It has these electrons that it can donate. And this is an ion. So this is going to act as a Lewis. Let's see. Okay. 1 second. Let's finish drawing. That's an ion with a 2-. This one has 2 non-bonded electrons here, and actually 6 for each of the oxygens. So let's look at what we got out here. This is a 2+, and SO3 is a 2-, right? So let's draw the Lewis dot structure for this one. That one won't have one, but this is a polyatomic ion. Remember, polyatomic ions are covalently bound. So the Lewis dot structure will give us some information about this one. Right? So sulfur is 6 and oxygen is 3. That's 4 times 6 is 24. Plus 2 is 26. Right? So we have sulfur, 3 oxygens, like 2, 4, 6 means 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so what's happened here? Well, this oxygen has a 2- charge. It has 6 valence electrons to start with, but now it's got 2 more because it's got a 2- charge, right? So what happened to these 8 electrons? These electrons were donated to that compound. And by donating these here, we formed that bond. Okay, so now we can answer the question. It took me a while to get there, but the electron pair donor is a base. So this is our Lewis base. It's donating a pair of electrons to form a bond. And sulfur, or sulfur dioxide actually, is accepting. This is the Lewis acid. Okay? It wasn't as simple as I thought at the beginning. We had to say, all right, this is where we're starting. Where are we going? Where are we going to end up? Since we end up here with this situation, then the focus is on those 2 electrons that started off over here. Now we know which one's which. This is a Lewis base. That's a Lewis acid. It could have, in some other reaction, sulfur dioxide could act as a Lewis base. But in this reaction, it acts as a Lewis acid. That was a tough one. How about 30? Okay, there's 30. Oh, answers are chopped off. Hold on a second. There we go. 30. Given the following values of pKa, determine which is the weakest base of the answers listed. Okay. Notice we've got these acids. So we're talking about probably the conjugate base of those acids. The only one that's missing is the chloride. And the chloride is missing because its pKa is so huge, it's virtually infinity, because hydrochloric acid dissociates completely in solution. Okay, and that should also inform our choice. If we didn't have this one, then we would compare these K values. And the weakest base comes from the strongest acid. So the strongest acid in this group is this one, HClO2. If those were the only choices, HClO2 would be our weakest base. But since we have chloride in there, coming from a very strong acid, then the chloride ion is the weakest base. Now remember what we mean by weak base. A weak base is one that will not, or is less likely. Hold on a second. Oh, I always forget to do this. There we go. My laptop battery was getting low. I forgot to plug it in. So back to the topic. The conjugate base of a strong acid. A strong acid produces a weak conjugate base. A weak acid produces a strong conjugate base. So if we had only these to go on, then the conjugate base here would be the strongest base of this group because it's from the weakest base, excuse me, the weakest base because it's from the strongest acid. And the strongest base would be from this one, HClO, because it would be the weakest acid. I'll come back to that one in a second. I got a point to make. But since we have the chloride ion here and HCl completely dissociates, which means that the chloride ion doesn't want a proton. It will not accept a proton, which means even if it encounters a water molecule, it won't take a proton from water. And that's what we mean by base. It's a weak base, which means it will not take a proton from water. Now this one, HClO, has 7.54. HClO. Has a pK 7.54. Right? What's the pK of neutral? Right. pK, well, actually, I think I'm barking up the wrong tree. Forget I said anything. I thought I was going to make a point here, but that it's not going to work. So, in fact, I'll probably chop that out of the video. Okay, that was 30, and the answer to this one is the weakest base is produced by the strongest acid, which is hydrochloric acid. So chloride ion is the weakest base. Let's look now at 38. 38 could potentially be a brain teaser. And scroll that one so we can see more of it. Okay, there's a lot of information in this right here. Question is, do we need all of it? Well, let's see what the question is. Carbonic acid is a diprotic acid, H2CO3. There's the Ka for the first proton, and there's the Ka for the second proton, right? It's got two acidic protons. The ion product for water, of course, that's a reminder. And what is the OH concentration of a solution of 0.18 molar sodium carbonate? Okay. So we're looking for the hydroxide ion concentration. That's the question. And the solution is made from that salt. Okay? And the concentration of that salt is 0.18 molar. Okay. That's all, that's information that's given, that's of immediate interest. And later we'll look at using these values, K values. But first of all, we need to say what happens when that goes into solution. If this is aqueous solution, what does it produce? Well, it produces sodium ions, actually two of them, plus a carbonate ion. Okay? So think of the acid-base equilibrium solution problems. What's the major species in this solution before any reaction occurs? Sodium ions and carbonate ions. Okay. So which one is going to react? Well, sodium doesn't react with anything. Right? We showed that in some ludicrous statements. Sodium reacting with water to produce something never happened. Right? And it's not going to react with carbonate because this thing is completely soluble, just breaks apart. So this is a spectator. This is the one we need to focus our attention on. So what reaction is that one going to undergo in water? This is what it's going to do. CO3, 2 minus, is going to react with water and produce one proton at a time. It's going to produce HCO3 minus plus OH. Oh, excuse me. Yeah, that's right. Minus, minus, two minuses, charges are balanced. And the reason I only did one proton at a time is for the same reason that you only dissociate an acid one proton at a time. And we look at the K values. This is the Ka for the first proton. But we're looking at the second proton. Right? The Ka2 is this one going to that one. So what we want to focus on is this value right here. But that's a Ka. That's a Ka for this one dissociating to that one. We want the Kb for this one. So we take the Ka of that one and we find the Kb for this one. So the Kb is going to be Kw divided by Ka2. Right? I'm pretty sure that's right. All right, so what is that value? Well, let's see, this is 10 to the minus 14, and this is 4.8 times 10 to the minus 11. Okay. So that Kb is equal to what? So we give a calculator. And we'll say 10 to the 14, minus 14, and divided by 4.8, yes, 10 to the minus 11. So that's 2.08 times 10 to the minus 4. 2.08 times 10 to the minus 4. That's the Kb for this reaction. Okay? Now, why do we need that? Well, we're going to set up an ice table. Okay? So, initial change equilibrium. What's the initial concentration of CO3 2 minus? Right here. The concentration of this species is 0.18. There's only one of these per molecule. So it's also the same concentration as that value. So we're starting off with 0.18 molar. Water doesn't count because it's infinite. It's pure. It doesn't even fit in that expression. How about this one? Well, when you first put this in, there's none of that. Right? There's none of that, and there's almost none of that. How do we know? Because the Kw for water is 10 to the minus 14th, and Kb is 10 to the minus 4. So this is the OH concentration determining reaction. Right here. Okay, what's going to happen? Which way is it going? It's going to shift that way, correct? It's going to make some OH minus. So when it does that, it's going to produce some of this and an equal amount of some of that. And then it's going to subtract that amount from here. Right? Okay, so we got 0.18 minus X. And over here we have X. Over here we have X. Okay. Now, what's our expression? Kb. Kb equals 2.08 times 10 to the minus 4 equals X times X. Right? This one times that one divided by this one. Now, and there's only one of them. So the exponents are all 1 minus X. Okay? All right, so what are we going to say? Well, this is a pretty small value, isn't it? Very small value. So compared to this, X should be very small. So we can say that this is approximately X squared divided by 0.18. Okay? So now that is equal to this value. So we take 0.18 times that value and take the square root of it. And that should give us the hydrogen ion, the hydroxyl ion concentration. So I've still got that one in my calculator. Let's multiply by 0.18. And then take the square root of it. So I get X equals actually the hydrogen ion concentration is 6.12 times 10 to the minus 3 molar. Okay. And that would be this one right here. That's the closest one to it. Now, in the worked problems, I go ahead and do the calculation to determine if this is a valid approximation. And it turns out to be like 3.5% difference, which is within the 5% rule. So this is a good value. Okay, that's number 38. And I think that's the last one I have chosen for chapter 14. Let me see if that's true. Yes, as a matter of fact. So now we can move to chapter 15. All right, chapter 15. I need to get a refill on my drink, so I'll be right back.
Okay.
Doing too much talking and my throat's drying out. Okay, I'm back. Let's switch over to chapter 15. That one. There we go. Let's see, and make that one bigger. About. And I'll do it. All right. So let's see, which one am I doing on this one? Let's start with number 4. If I can page to that one. Yeah, there we go. For a weak acid, HF, is in solution with a dissolved sodium fluoride. So we have this in solution, and we have also that one in solution. If hydrochloric acid is added, okay, so we're going to add HCl. Okay. Which ion will react with the extra hydrogen ions from HCl to keep the pH from changing? Okay. So this is going to produce hydrogen ions. Okay. So what are we saying here? If these two are in solution together, what are the ions that are active in a sense of hydrogen ions and hydroxyl ions reacting? This is going to be a spectator, right? So it's not going to react with anything. So we've got HF and F minus, right? How are they related? Like that, right? The dissociation of a weak acid, right? It's mostly over here, right? If it's a weak acid, mostly here. So when we put these extras in here, which species is going to react with the hydrogen ions? That one right there, right? Le Chatelier says when we add extra this, then the reaction goes back that way. So hydrogen ions plus F minus. F minus is the species that reacts with the extra hydrogen ions. Okay? What if, while we're here, what if we had hydroxyls? Instead of that, what if we had sodium hydroxide? Right? those hydroxyl ions, what are they going to react with to keep the pH constant? Well, they're trying to drive the pH basic. Okay? So we've got this same reaction. This one is going to react with that one and make water. Correct? So that removes hydrogen ions from this reaction. And then the reaction is going to shift back this direction to produce some more hydrogen ions. Okay? So that's how bases are consumed by a buffer. That's what we're talking about here, a buffered solution. Let's see, that was 4. Yeah, I want to do 5 also. Let me scroll that one up. Okay. Oh, this is definition. Which of the following is true for a buffered solution? Think about the definition of a buffer. Right? What does a buffer do? Well, in an acid-base sense, a buffer, for the addition of hydrogen ions, acid or base, either one, the pH of the solution changes minimally, very little. It's not fixed. The pH will change some, but it will not change as drastically as it would if you put the acid or the base into pure water. Okay, so the buffer tends to maintain the pH in a narrow range. All right, so which one of these satisfies that condition? The solution resists change in its H+. Well, yeah, that means pH doesn't change very much. Okay, how about this one? The solution will not change its pH very much even if a concentrated acid is added. That's another way of saying A. The solution will not change its pH very much even if a strong base is added. Well, yeah, that's true also. Any hydrogen ions will react with a conjugate base of a weak acid already in solution. That's true. The conjugate base of HF from our previous example is F-, and the hydrogen ions react with that conjugate base of the weak acid HF. So as an example, that confirms this statement. So all of them are true. All of those statements, all 4 of them are true. All right, that was 5. Let me see. How about 8, 9, and 10. Let's see. Let me scroll just a little bit so we can get 8 and 9 on there. And maybe when I page, I'll get 10 without having to walk over to the computer. 8. How do the pHs of the buffered solutions compare? Oh, sorry, that's based upon this previous statement. You have 2 buffered solutions. Buffer 1 consists of 5 molar acetic acid and 5 molar sodium acetate. So is that a good buffer? I mean, is it in the buffer zone? Well, yeah. When the acid and the conjugate base are equal in concentration, remember Anderson-Hasselbalch? And this one is, I'll write it this way, conjugate base over the acid, or weak acid conjugate base. So when is this in the perfect buffer zone? I say we're adding base for this acid. It goes like this, and then it goes like that, like that. The perfect buffer zone is right here. And that, if this is equivalence, then this is 1/2 equivalence. And where is 1/2 equivalence? That's when only half of the acid has been consumed. So if you got an equal amount of acid and base, that's the pK. And that's the perfect dead center of the buffer zone. So yeah, if you got equal amounts of acid and base, and equal amounts here of acid and base, right? Both of those are in the middle of the buffer zone. But there's a difference, correct? Right? It has to do with buffer capacity. Which one has the greater buffer capacity? Well, the one with the higher concentration does, right? It can stand up to adding more acid or more base and maintain its pH with higher amounts of acid base added. Whereas with this one, it won't last very long. It'll maintain its pH up to a point, and then when its buffer capacity is exhausted, then the pH will change drastically. Okay, so with that knowledge, let's look at 8. The pH of buffer solution 1 is greater than that of buffer solution 2. No, we haven't done anything to it yet. They're both exactly in the middle of the pH range. They're both the same pH, exactly the same, right? Because this ratio, 1:1, makes that term go to 0, right? If this is divided by itself, then that's 1, and 10 to the 0 power is 1, makes this term 0. So they both have the same pH. So A is false. The pH of buffered solution 2 is greater than that of buffered solution 1. No, that's not true either. Like I said before, they're both the same. How about this one? The pH of buffered solution 1 is equal to that of buffered solution 2. That is true. And that's just thrown in there. That statement is thrown in there to confuse. Cannot determine? Oh yeah, we can. How do the pHs compare? We can't determine the pH without the K value, but we can compare them, right? And they're both equal. So C is the true statement out of that group. Let's see, I'm going to look at 9 also, don't I? Yeah. Which of the following is the net ionic equation for the reaction that occurs during the titration of nitric acid and potassium hydroxide? Nitric acid and potassium hydroxide. What do they yield? They always yield a salt plus water. What's the complete ionic equation? Well, in solution, this is hydrogen ions plus nitrate ions plus potassium ions plus hydroxyl ions. They're all in solution. And this one is potassium ions plus nitrate ions plus water. Okay? So how do we write the net ionic equation? Well, that's the complete. So we look for spectators, right? There's one. There's another one. So what do we got left over? H plus OH minus yields water. That is the net ionic equation for all acid-base reactions, as long as they're Arrhenius type, where they have hydroxyl and hydrogen ions. Okay. I'm not so sure about ones where you have Well, actually, yeah. I was thinking of ammonium. Ammonia and water. When you put ammonia in solution, you get ammonium plus hydroxyls. And then when you add acid to that, say HCl minus, then you get ammonium chloride and H plus and OH minus equaling H2O. So yeah, it works for non-Arrhenius bases as well. Okay, so the moral of that story is the net ionic equation for every acid-base reaction is H plus OH minus yields water. And since we know the K value for this reaction, for the reverse reaction, the K value for this reaction is 10 to the 14th, not 10 to the minus 14th. 10 to the minus 14th is going this direction. 10 to the 14th is going that direction. So it wants to be water to 14 orders of magnitude. That's how strong the drive is to produce this. And that's the driving force for any acid-base reaction, the production of water. Okay, that was 9. Let's see, what do I want to go to next? 10. We'll get 10. And we won't get 10 until I scroll it. There we go. Okay, in a titration, there's that word. What's a titration? A titration in the acid-base sense is the measured addition of an acid to a known amount of base or a base to a known amount of acid to determine how much of the unknown there is. Right? So if the unknown is acid, you're adding a known concentration of base, then eventually you can calculate how much acid you have, and vice versa. So in this titration of a weak acid with 0.1 molar sodium hydroxide, the stoichiometric point is known to occur at a pH value of 10. Stoichiometric point. Let's look at that. So we're going to titrate with 0.1 molar sodium hydroxide. And our acid starts here. Looks like that. Why? Because it's only got one proton. You've only got one step in a single proton acid. If you have 2 protons, then it'll do a double step like that. Or if you have 3 protons, like phosphoric acid, it'll do 3 steps. But we're only looking at 1 step here. Okay. So what we're saying is, with this concentration of sodium hydroxide, the stoichiometric point is known to occur at a pH value of 11. The stoichiometric point is right here. And that is pH 11. Okay, that's given right here in the problem. Which of the following indicators would be the best to use to mark the endpoint of this titration? Well, we have 2 choices. What you try to do, and all indicators are weak acids, right? They have their own equilibrium going on at the same time as your titration. So what you try to do is pick the indicator where the Ka is closest to the Ka of the equivalence point of your reaction. And the equivalence point is 11. So we should go for, in fact, I wonder, if that's even correct. Because I would expect the pK to be used at pK 11. Okay, let's see. Okay, here's the reasoning. Notice that the Ka for this indicator is 12, 11, and the Ka for this one is 12. All right. Remember what we said about the physiological response to color change. The color change, as far as human eye is concerned, occurs over a pH range of pKa plus or minus 1. Right? So for D, that range would be, well, pKa would be 11, right? So it'd be 11 plus or minus 1, which would be a range of 10 to 12. Right? And E would be 12 plus or minus 1, which would be 11 to 13. Okay, here's the reasoning. If we use this one, and notice we're coming up from underneath, we're coming from a low pH up. Right? So we're coming up from underneath here. We're coming 7, 8, 9, 10. 7, 8, 9, 10, 11. Okay? This is when the pH starts to change. It changes, the color. The color change occurs over this range. All right? So when you're coming up from underneath, you want to be able to detect the color change as soon as possible, close to the equivalence point of 11. Okay? And in order to do that, the pH has to start changing near that point, 11. Okay? Here, the pH, the color change will already be well underway by the time you get to 11. And you may mistake it for down here somewhere, down here, right? So that increases your error. So what you want is when you're coming up from the acidic side, you want the pH change to be here, starting at 11. Okay, that's why E is the better choice here, rather than this one. Okay, now if we were doing a titrating a base with an acid, that would be coming down from the other direction. And in that case, you want the start detecting the color change from the basic side. So in that case, with the same, if we were doing that titration the same here, looking for 11, we would want to come from the high end. So we would want to come from this one. Actually, we'd actually want to use this one. It pH changes from 9 to 11. So A would be better for this one. Right in here. So A would give us a change. This one would start changing at 11 from the other side. Okay. And we wouldn't even look at this one at all. It would either be this one for the acid titration or this one for the base titration. Excuse me. If we were titrating with a base, we'd use this one. Titrating with an acid, we'd use this one. Okay? That's the reasoning behind the answer to number 11. Wait a minute. I've been looking at the wrong one the whole time. That should have been number 11. Did I just forget to write the number? No. I was doing number 11. I'm sorry. I was discussing number 11 here. And I should have stayed on number 10. Okay, that's number 11 discussion. Now let's go back to 10. Get my head screwed on straight. Now we will go back to 10. In the titration of weak acid with 0.1 molar sodium hydroxide, so we got the same scenario. The stoichiometric point is known to occur at a pH value of approximately 10. Which of the following indicator acids would be best to use to mark the endpoint? Okay. So it's a similar discussion. 10 is a similar discussion. In this case, we're titrating an acid, a weak acid, both cases with 0.1 molar. All right, so we have the same type of, this is base, and this is our pH. And we're going like this, like that. So we're right in here. And that occurs at a pH of 10. Okay. So now, since we're coming in from the underneath, we want one that has a range of 10 to 12 because we want to start picking up that color change at 10 or very close to 10. Okay, so where would that be? Well, that would be this one right here. Right? The pKa for that one would be 11. And that would mean pKa equals 11 plus or minus 1 is the range color change. So we're coming up from 10. Right? That's why B is the answer for this one. Okay? So it wasn't totally wasted. I was just talking about the wrong one the whole time. All right. That was 11, 10 and 11. How about 13? Let's see what 13 looks like. 13, which would be described as a buffer solution. 13. Okay. In order to have a buffer solution, you need to produce by some way a mixture of the weak acid and its conjugate base. So it looks like, let's see, these we're starting with acetic acid, right? That's the alternate way to write acetic acid. HC2H3O2 is equal to CH3COOH. The same molecule, just written differently. We write it this way so that we can see that's where the acidic hydrogen is located on the molecule. It's a carboxylic acid. It looks like this. Let's see, C, H, 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 C, O, O, H. So there's your acidic hydrogen. Okay. So in order to make a buffer solution, you need two conditions. You need a mixture of the acid, the weak acid, and its conjugate base. You need those two together. In this case. Right? So we'll look at the others and see if that's true for those also. Right? So do we have here or here If you add this strong acid to that weak acid, what are you going to get? Well, you're going to get an acidic solution. That's it. You're not going to get a base. You're not going to free up any conjugate bases out of that, right? Because you're adding more protons, and that's going to keep any of this in that form. It's going to make less of this, actually. So A is false. A cannot be. How about the next one? If we do this and react it with sodium hydroxide, what is that going to do? Well, sodium's a spectator. So this is the reaction that's going to occur. Right? So this is going to produce water plus C2H3O2 minus. Okay, we met the first condition. By adding this base to that acid, we're going to convert some of it into that conjugate base. Now we have some of those in solution. And if we do that, then this is going to react with, let's see, it's 1-to-1, hydroxyl and acid. So this is going to use up a lot of that, but not all of it. There will be some left over. There will be 0.05 molar of this C2H3O2, and then we will have freed up 0.2 molar of this. Now, it's not going to be right in the middle of the range, of the buffer range, but it will be in the buffer range, just on the fringe. And it's still technically a buffer. Okay, so that's a possibility. In fact, that answers the question. We will make a buffer with that. But why are these others not buffers? Sodium bromide and HBr. Right? Well, bromine, HBr is not a weak acid, so it can't make a buffer. Right? Throw that one out. NH3 and NaOH, you've got a base and a base. You can't make a buffer out of that either. How about this one? A strong acid and a strong base, but you're just going to get a pH change. You're not going to get a buffer because there's no weak acid in there to make the conjugate base. Right? So this is the only one that works right here. That's the best answer. It's not a good buffer, but it is a buffer. Let's see, 13. Let's see, 13, 14. We'll look at 14 also. Okay, let me see, how am I doing on time? Okay, we're good. Which of the following mixtures would be classified as a buffer solution? So we're looking for the same satisfy the same set of conditions to make a buffer here. We need a weak acid and its conjugate base. So that's a strong acid, won't happen. This is a weak acid, yeah. And if we react with 55 mils, equal concentrations of acid and base, if we add 55 mils of this base to 55 mils of that acid, both at the same concentration, we have exceeded the equivalence point for that by 5 milliliters of base. This is going to be a basic solution and not buffered. It's going to be on that. It's going to be past this and up in here somewhere. You're way beyond buffer. Right? So this one can't work. How about this one? 50 milliliters, 0.1 molar, and 25 milliliters. That's perfect. You're only neutralizing half of this acid and producing its conjugate base. in equal amounts. Now, since you've used up half of it, you're producing half of it as the acetate ion, and the other half is staying as the weak acid. That's a perfect buffer. It's conjugate base divided by weak acid is the same concentration. They're equal, simply because we neutralized only half of it to make the conjugate base. This is perfect. That is our buffer. Now, if we looked at, let's see, this one, we just add a little bit of base to this acid. You're still in this part, right down here. You're nowhere near the buffer zone when you've added just a little bit of base, right? So that one would work. How about this one? Adding acid to acid? No. Add acid to acid, you get an acidic solution, not a buffer. Right? So that one, the only way that one is satisfied is with this perfect solution right here. Okay. That was 14. Where to next? 19. 18. 19. Yeah, we've got everything up there. Okay. 19. We have these indicators to choose from. Right? And rather than having to go from the rule of thumb, pKa plus or minus 1, we're actually given the pH range for these buffers, 3.2 to 4.4. Right? So it's the color changes in between those. Starts here from the acid side and goes there and is complete by 4.4. 4.86, that's a little wider range. 6 and 7.6, that's a wider range. Wider range. This is a very wide range. Actually, that's a good. 10.1 to 12 means that the pK for that one is about 11. But this gives us our pH range. Now, for this one, we're going to say, assume an indicator works best when the equivalence point of the titration comes in the middle of the indicator range. Now, this one, you're actually given those conditions. I mean, if we weren't given these conditions right here, I would say if you're titrating an acid with a base, then I would look for equivalence point near the lower end. But we're given these conditions, so we have to go with them. Which of the following titrations would methyl red be the best indicator? Okay. Let me see. I don't want to waste a bunch of time, so I'm going to check myself. In order to answer this one, we need to know the pH at equivalence. And that's going to take some doing. In order to know the pH at equivalence, we have to actually work out that value for each one of these. Okay? So the first one is the easiest one. The first one has a strong acid with a strong base of equal concentration. They are going to be equivalent. Their equivalence point is exactly 7. Okay, so we're looking at methyl red. Methyl red is 4.8 to 6. So what's the middle of that range? 4.8, 6 is 10.8 divided by 2 would be 5.4 pH. So we're looking for 5.4 pH. We want that to be our equivalence point. All right. So we've got this next one where we have an aniline with a Kb of that value and HCl. So let's see. We don't need to know what an aniline is. We just need to know that the aniline conjugate base, the conjugate base for aniline, whatever it happens to be, we're going to pick up a proton from somewhere and produce this one. Okay? So the proton we're going to pick up comes from hydrochloric acid. But when we start out, this is our KB reaction. And let's see, before we write that, what's our ice table look like? Well, we have 0.1 molar of this, 0.1 molar. Right? And actually, if we're adding 0.1 molar aniline and 0.1 molar HCl, that means we have equal volumes. Right? So this initial concentration is actually going to be cut in half because we add the same amount of volume of this one as we do that one. So that's our starting point. And this is the type of problem solution that requires that you first, when a titration is involved, you first go to completion. Let the reaction go to completion, then work your way backwards to the pH. So at completion, we would have this, and we would have none of that, right? Because we've used it all up. We used it all up to make this. Oh, wait a minute. Yeah, that's true. That's true. Oh, we've neutralized this one. Okay, I've got it backwards. We've neutralized this one, and we produced this one. So now in solution, we have this one is going to yield that plus that. So now we have initial concentration here of 0.1, which we produced by that titration, divided by 2. And we're saying that now we have none of those. So that means the equation is going to go back, change, is going to make some of this and some of that. And this is going to be 0.050 minus X. Oh, excuse me. Let's go minus X. Now the equivalence is 0.050 minus X. This is X. This is X. Okay. So we let the reaction go to completion and it produced all of this. Now what happens? In solution, it partially dissociates. Well, what's the, there's the KB, but this is not KB, this is Ka, correct? Yeah, we need a Ka for this one. So what's the Ka? The Ka is 10 to the minus 14 divided by 3.8 times 10 to the minus 10. And that should be, if the calculations were done correctly, 2.63 times 10 to the minus 5. So that's the K that governs this reaction. And this is going to be equal to X squared divided by 0.050 minus X. Now, with this value of Ka, how big is that X going to be? It's not going to be very big. So we'll say that goes away, and this times that, take the square root. And you should get X equals 1.15 times 10 to the third power And then if we do the negative log of that value, then we should get a pH of 2.94. Right? 2.94 is way far away from that value. This indicator would not be good for that one. So B is out. B is wrong. Okay. So we'll say B is wrong, A is wrong. How about C? Let's see here. So what do we have with C? We have 0.1 molar ammonia plus 0.1 molar HCl. Right? So our first reaction is this one plus this one yields NH4 plus Cl minus. So we let the reaction go to completion, right? Equal amounts. We go to completion, and now we have this one in solution. Actually, based upon that previous reaction, this is going to make H plus NH3, right? And we're starting off with the same, right? All of these are the same concentration and equivalence. And we've taken 0.1 molar and cut it in half, right? So now we're going, this is the equilibrium part. So the change is going to be similar. Plus X, minus X. And that's 0.050 minus X equals XX. And now this is actually a Ka because we lost a proton. And do we have a Ka? No, we have a Kb. So we need to calculate the Ka for this reaction, which is what? Ka equals 10 to the minus 14 divided by 1.8 times 10 to the minus 5, which is equal to 2.36 times 10 to the minus 5. Oh, no, it's not. What is that value? I gotta calculate that one. Okay, 1 exponent 14, 1.8 exponent 5, same. But this is 5.56 times 10 to the minus 10. And that's equal to x squared over 0.050, because we say that x is too small, right? With this value, x is going to be so small that now we just multiply this times that, take the square root, and x is equal to 2.36 times 10 to the minus 5. And the negative log of that gives us pH of 4.63. Okay, so that's a candidate. We're getting closer. So C is pH 4.63. All right. What's D? Let's see. D is HF with sodium hydroxide. Okay, and the Ka of HF is this value right here. Okay. This is similar to the aniline. We've got the Ka. Actually, Ka is what we need. No, Kb is what we need. Why? Well, what you've got is your HF is plus sodium hydroxide. Okay? So at equivalence, all of this is shifted over here to this, and you've got water plus sodium fluoride. Now, sodium's a spectator. Fluoride is our ion of interest. So now that we've got the stoichiometry done, the concentration of this is now 0.1 divided by 2, because we have equal volumes of each one of these. Right? So there we are again, 0.05. Now the reaction is fluorine plus water yields, and that's equilibrium, yields HF plus OH minus. Okay? So this is the equilibrium. This is the stoichiometry. This is the equilibrium that follows it. And the initial change equilibrium here. This one is 0.050. Water doesn't count. HF, we haven't made any yet, and OH minus, we haven't made any yet. So what's the change? Well, we're going to get some of this, we're going to get some of that, and we're going to lose some of this. So we have 0.050 minus X, and we have X and X. This is Kb. What are we given here? Ka. So we need Kb. So Kb for that expression is 10 to the minus 14 divided by 7.2 times 10 to the minus 4. Okay? So what is that? Well, let's see. Did I do it here so I don't have to? No, I didn't do it. All right, so 10 to the minus 14 and 7.2 10 to the minus 4. That would be 1.39 times 10 to the minus 11. So our expression is this one equals X squared over 0.050 because I dropped the X again. So now if we solve for X in this one, what is X equal to? X is equal to hydroxide. So that's equal to 8.33 times 10 to the minus 7. POH is negative log of that value, which is 6.08, and pH is 14 minus that, which is 7.92. So D is pH 7.92 at equivalence. And that's way far away from our target. Now, acetic acid and sodium hydroxide. All right. That's the last one. I know I'm taking a lot of time to do this, but it just illustrates the ability, if you have all the information you need, to determine the pH at equivalence for any of these reactions. So for E, we've got 0.1 molar acetic acid plus sodium hydroxide. Right, so when we reach equivalence, what do we have? Well, we've got acetic acid reacting with sodium hydroxide. This is the stoichiometry. So this will go to water plus sodium acetate. That's how I abbreviate acetate, OAC. All right, now what we've got is sodium acetate. We've got the acetate ion at equivalence. So this is stoichiometry. Equivalence is acetate ion, and I'll write this one out. Reacting with water, right? And that's an equilibrium. Stoichiometry, equilibrium. To give us acetic acid plus OH. And that requires a Kb to determine the pH. And we've got a Ka. So the Kb is equal to 10 to the minus 14 divided by 1.8 times 10 to the minus 5, which is equal to 1.8 10 to the minus 5 is 5.56 times 10 to the minus 10. That's the Kb for this reaction. We have initial, change, equivalence. So we've taken everything, just like before, taken it to the right, and now we've diluted it half strength. So we're starting off with this molarity, nothing there, nothing there, nothing there. And this is going to be plus X, minus X, and we have 0.050 minus X. This is X and X. So this value, this Kb, is going to be equal to X squared divided by 0.050 and X. Notice I dropped the X again because it's so small. This value is so small, we're not going to have much X. And X is going to be 0.05 times this value, take the square root of that product, and X is equal to 5.27 times 10 to the minus 6, and that's equal to OH minus. So the POH is equal to 5.28, and the pH is 14 minus that, which is 8.72. Okay? So E is 8.72 pH. That's way far away from 5.4. So the best one out of this group is C, 4.63, is where that one will occur. The equivalence will occur there. Now, if we were doing this titration in the lab, which we're scheduled to do today, we would find that once we've plotted our titration, we would find that that part, this part right here, would occur at 8.72. We're very close to it. Okay, and that's why we use phenolphthalein for most of the reactions, because 8.72 is very close to where the color change starts. That's why phenolphthalein works extremely well as an indicator for this type of reaction. Now, other type of reactions, it may be a little further afield, but it's still pretty good. All right, that was 19. Let's see, how much time we got? I'm about out of time. Let's see, 23 and 25 are the last two. Well, we can do them, right? Because there's nobody here to do the lab. So we'll just finish it through our lab play, our lab time. a 50 milliliter solution of 0.035 molar hydrocyanic acid, and there's your K value for that one, is titrated with a 0.0333 molar solution of sodium hydroxide as the titrate. Is this going to work? Yeah, that's an acid and this is a base. So we can titrate them. What's the pH of the acid solution after 15 milliliters of titrate have been added? And there's the reminder of the KW. Okay. So what are we given? Well, we're given 50 milliliters of hydrocyanic acid. Oops, there. Hydrocyanic acid. Oh, and the K for hydrocyanic acid, its dissociation constant is 6.2 times 10 to the minus 10. Okay, that's given. And we're titrating with 15 milliliters. 15 milliliters of 0.0333 molar sodium hydroxide. Okay? What's the pH of the solution at that point? All right. So what we have here is first the stoichiometry of the reaction. So what reaction are we observing in this titration? Well, what we see is HCN plus sodium hydroxide yields sodium cyanide plus water. Okay? Before we start the reaction, and sometimes, in fact, this method that I'm going to use is going to be useful when we work with complex ions. And that'll be the lab after this one. Next week, I'll give that one to you. Or you can look it up in Blackboard, it's there. So for the stoichiometry, sometimes it's more useful to stick to the moles of the reactants rather than concentration. So in this case, how many moles of hydrocyanic acid are there? Let's see, I left out something. 0.0350 molar. 0.0350 molar hydrocyanic acid. There we go. Okay. So, and also, I'm going to use a trick so that I don't have to change milliliters to liters to produce moles. I'm just going to multiply 50 milliliters times that concentration, and what will that give me? Millimoles. Milliliters times molarity yields millimoles. So before the reaction starts, what do we have? Well, we have 50 times 0.0350. 50 times 0.0350. And that's equal to 1.75 millimoles. So it's 1.75 times 10 to the minus third moles. That's all that is. And how much sodium hydroxide? And I kind of overlapped here. How much sodium hydroxide do we start with? Well, we have 15 milliliters times 0.0333, which is equal to 0.4995 millimoles. That's before the reaction. After the reaction, what do we have? Well, look at the difference here. It's 1-to-1, right? One hydrogen, one hydroxyl means they're equivalent in their normality. So this one is going to completely be consumed over here. Right? So this one's going to go to 0. And this one's going to be what's left over after all of that consumes some of it. So this one is going to be 1.75 minus 0.4995, which is equal to 1.25 rounded off millimoles. Okay? That's the stoichiometry. The stoichiometry of the titration. Now we have a starting point for the equilibrium. We've used up all the sodium hydroxide, so now what do we have? Well, not only do we have used up this, but we also have produced that much, that much sodium cyanide. So after we have 0.4995 millimoles of sodium cyanide. Okay, so notice what we have. We have a weak acid and its conjugate base. Okay, now we have that many millimoles. What's the concentration? Now, when we set up equilibrium, we have to work in concentration. This absolute amounts works fine for the stoichiometry, but for the equilibrium, we need to define the equilibrium reaction. Okay, what are the major species? Well, we've got HCN, we have CN minus, so we've still got acid being dissociated into CN minus. So let's make room for the equilibrium. So for equilibrium, what do we have? We've still got HCN, we have some CN minus, but we have enough of this that it's going to continue to be a major player, right? A major species in the reaction. So when we're looking at that, we're getting this plus that, right? And now we know that the initial concentration of this after the stoichiometry is 1.25 millimoles divided by milliliters, which will give us molarity. And the volume now is not 50 anymore. It's 50 plus 15, which is 65. Right? Which is 1.92 times 10 to the minus 2 molar. Okay? And we also have 0.4995 divided by 65, which is equal to 7.68 times 10 to the minus 3. And we don't have any of that, at least none appreciable amount, because this value is much larger than 10 to the minus 14 for water. So water as a competing reaction will have no influence on the pH. Okay, that's our initial. What's our change? Well, since we don't have any of that, it's going to make some of that. Right? And it's going to lose, it's going to, let's see, it's going to make some of this too, because where it's coming from here, making that and that, and then we're going to lose some here. Okay. So now we have 1.92 times 10 to the minus 2 minus x, and then we have x and x. All right, so we need the Ka for this reaction. Do we have it? Let's see, 23. Ka, there it is. Ka for hydrocyanic acid. All right.
So I'm going to have to erase this one just to make room. So the Ka, or hydrocyanic acid, is 6.2 times 10 to the minus 10. And that's equal to x squared. Oops, wrong. 7.68 times 10 to the minus 3 plus x. So this is 7.68 times 10 to the minus 3 plus x times x divided by 1.92 times 10 to the minus 2 minus x. Okay, so now we have to solve for x. Are there any shortcuts we can take? Actually, the x change in each of these cases is going to be so close in size to these, we can't. We're going to have to use quadratic. So if we resolve this one, let's see. Well, okay. You would take this one and multiply by that. So that times this minus that times that on this side, which should be this 1.19 times 10 to the minus 11 minus 6.2 times 10 to the minus 10 x. That's this one times that one. And on this side, we have x times these values. 7.68 times 10 to the minus 3 x. Actually, need that. Plus x squared. Yep. And then if we put everything on one side so that we have 0 on the other side, which is the way you solve a quadratic, you got to have all the terms on one side equal to 0. We have x squared plus 7.68 times 10 to the minus 3 x minus 1.9 times 10 to the minus 11 0. So what we did was to keep this one positive and that one positive, we hold on a second. Is that right? Oh, okay. You see what I did here? Here's your x terms right there. When you add this to both sides, put this one over here and add that to that, what effect is this one going to have on that one? 10 to the minus 10th and 10 to the minus 3. Nothing. So actually, you can throw that one out. And now, these two terms are positives. And then you have this one, which went over here as a minus. So actually, I just flipped the equation. After I put this one as a minus over here, and rearrange them, then the 0 would be on this side, but it's easier to visualize it because this is going to be the A term, this is going to be the B term, and this will be the C term for our quadratic solution, right? And you remember, let's see, minus B plus or minus square root of B squared minus 4AC divided by 2A. Okay. So if you plug in these values in the correct position and solve for X, you're going to get two numbers. And you have to decide which one makes sense. And we're not going to go through that. But the solution now will be X, which is equal to, X is equal to the hydrogen ion concentration. So once we solve for X, we have our answer in terms of hydrogen ion concentration in the -9 mole. And then pH is equal to 8.81. So we went around the barn several times to get this answer. And let's see, I hope 25 is not quite as lengthy. Let's see. I'm glad this is being recorded too. 25. So let me scroll that one. There we go. All right. A certain indicator, HIN. Yeah, a certain indicator, HIN, has a pKa of 9. So what does that mean? Remember, indicators are weak acids. So during the reaction, they proceed with this type of reaction. And this will be one color, like this will be color 1, and this will be color 2. You can tell the difference between them. And the pKa for this reaction is 9. Okay? At what pH is this color change visible? When 7% of ion minus. When we reach, this is converted into 7% that, then we can see the pH change. At what pH change does that occur? Okay. So what does that mean, 7%? That means this ratio to this one times 100 equals 7%. Okay? Well, it might be easier to take that 100 and put it over here. So percent divided by 100 is actually a fraction. So that is equal to 0.07. Okay, that's all I did. I just divided both sides by 100. Okay, so we're going to make this easy, right? And thanks to Henderson and Hasselbalch, it is easy. What's the pH when we know this ratio? Oh, excuse me, plus the log of, oops, wrote that wrong, IN minus divided by H. Okay? And we want to know what pH, at what pH does that take place? This is 9.0. And this is 0.07. Right? So we just need to take the log of that value and add it to this one. and find out what the pH is. And if we do, this term is minus 1.15. So the pH is 9 minus 1.15, which is 7.85. So 7.85 is the pH. Well, the nearest answer is 7.88. Now, if you see something like this on a test, you know, you're perfectly within your rights to say none of these. Right? If you see 7.88, because that's definitely not 7.85. But if you put D as your answer, I'm going to take it right. And if you put E, in this case, for your answer, I'll take that right also. Okay, I think that's all the ones I had picked out.